And the next talk will be by Phil Mocz, who will be telling us about moving mesh magnetohydrodynamics and applications to star-forming cores.
Okay, hello everyone. My name is Philip Mocz. I'm a graduate student at Harvard University, and I'll talk about simulating star-forming cores with a moving mesh magnetohydrodynamic code. This is work I'm doing in collaboration with Blakesley and Chat, who are both at this conference, and my advisor is Lars Hörnquist. So I come from a cosmological simulation background. Okay, so before I begin to talk, just to give a big overview of the types of simulations we're doing, I'm simulating isothermal ideal MHD turbulence and switching on self-gravity to form these star-forming cores and create mock observations to explain CARMA and ALMA scale data. And this morning, Chat, I showed you some exciting observations of these cores where you have very complex morphology and topology of the magnetic fields, and we hope to explain this, this morphology with simulations. Okay, so the outline of my talk has 3 parts. I'll motivate with some observations, then I'll describe the numerical method, and finally explain the results of my simulations. So background, we all know at this conference that star formation has at least the key ingredients of turbulent self-gravity and magnetic fields. And the type of, the scenario I'm looking at here is core collapse, which is generally true for when you're in the supersonic, super-alphanic regime. And here you can have direct collapse of these star-forming cores. There are also alternative theories, such as having a strong mean field, where the cores can form by ambipolar drift, which we've heard about at this conference too. But with this direct collapse, characteristic morphological signatures include the hourglass shape, signifying magnetically dominant fields in that region. So of course, the origin of magnetic field structure, it's a question there's a question of how much is the large scale magnetic field impacting the smallest scales, and whether the smallest scale magnetic fields can be instead modified by local turbulence. And this is referred to as the magnetic topology problem in the literature by people like Chris. So we can ask, how does the contraction happen? How does the contraction of these cores happen? And we've heard a lot of debate at this conference between studying how the magnetic field scales as a density. And usually you can assume some power law, and depending on the degree of anisotropy of the collapse, you can have a scaling that ranges between 0 and 1. For the case of a weak field or isotropic collapse, you have a scaling of 2/3. And for an anisotropic collapse, you can have a scaling of 1, of 0, or 1/2. The case of 1/2 is interesting because for isothermal gas, it means that you have equipartition between your magnetic pressure and your gas pressure. And so how simple is the formation of star-forming cores? So these observations in the Nature paper by Lee et al. 2015 study the formation of massive star-forming cores from the 100 parsec scale down to 0.1 parsec scale with the SMA. And they find dynamically important P fields, these characteristic hourglass shapes, on several scales, from 100 to 0.1 parsec. And they find a scaling between the magnetic field and the density of 0.4, signifying anisotropic contraction of these cores. And what about smaller scales? So when you have data and higher resolution data, look at the details with better resolution, things become more complicated. As Chad has shown this morning, the Serpens core, we see complex filamentary structures. We do see some pinching. We see clumps. We see features that are not part of the traditional hourglass shape. So what I'm interested in is in using these high-resolution moving mesh simulations to predict the morphology of these cores, really get down to these ALMA scale resolutions, see if we can predict the morphology with a code that has been used classically in cosmological contexts to predict the morphology of galaxies. So on to part 2, describing the moving mesh code. I use the Arepo code, which is it's a very unique code. It's a Galilean invariant code that uses a moving mesh, which means that you reduce advection errors completely. In fact, if you solve an advection problem, it's exact. And you have automatic spatial adaptivity of these cells. I'll show you a movie in the next slide. And what I primarily worked on for my PhD is adding magnetohydrodynamics to this hydro code. And this actually turns out to be non-trivial and complicated due to the moving mesh nature. In particular, you have to preserve the divergence of the magnetic field to 0, which is one of Maxwell's equations. There's many ways to do this, including divergence cleaning schemes, which turn out not to be so good. And you need to actually preserve this condition at the discretized level using a generalized constraint transport algorithm. Okay, so this is what the moving mesh code looks like. On the left, simulating a Kelvin-Helmholtz instability. On the right, just showing a disk, and you can see really the range of automatic spatial adaptivity of this code. And the advantages of my MHD code include we have a machine precision control on the divergence errors. So here shown in blue compared to cleaning schemes, which have order 1% errors. We also have exact advection. So this is a magnetic field loop, just advecting with the flow, and there's no diffusion. You get diffusion on both static grid codes or with cleaning schemes. So this is particularly relevant for high Mach number simulations. Finally, I want to point out that cleaning schemes give incorrect jump conditions for strong shocks. So my method is described in my 2014 paper, and this new paper that reformulates the same method as a cell-centered vector potential formulation for more efficient implementation. Okay, and just to point out issues with using cleaning schemes compared to constrained transport schemes, you can actually artificially grow your average magnetic field if you use a cleaning scheme compared to constrained transport. Okay, so part 3, the simulations. So here's the setup of these simulations. Here's a fiducial case. We run a box with 256 cube particles. Each particle has a mass resolution of 10 to the minus 5 solar masses. We switch on gravity and run for approximately 1 free fall time. These simulations are isothermal. I set the Mach number to 5, alphanic Mach number. I varied the initial field, so this particular case has alphanic Mach number 2, alpha variable parameter set to 1, and we form cores such as this one shown here, which we studied the morphology of. Just the size of the boxes, roughly 2 parsec, few hundred solar masses. Okay, and these simulations are what I like to consider really an upgrade to the standard spherical isothermal model of collapse. So the famous classical Larson 1969 paper described this spherical collapse, but on top of this we add self-gravity and turbulence, and we get the conversion of we get to study the amplification of the magnetic fields and the conversion of gravitational potential energy to turbulent energy. Okay, so this is just showing the turbulent box and just a very small chunk of the box and the collapse of features. So there's going to be a feature coming in here. This is showing the density PDF. Starts off as log normal, which is characteristic of turbulence, and develops this nice -3½ power law tail due to self-gravity. And here is shown the phase space of the magnetic field versus the density, and plotted our lines for slope 1/2 versus 2/3. So initially in the turbulent box, before self-gravity is turned on, there's no strong correlation, but you can see once there's collapse, the correlation develops. So again, here's the density PDFs, which is well understood. And here is the phase space for showing all the gas in this box. And we find some signatures of anisotropic contraction, B scaling roughly 0 to the 1/2 on the highest density scales. But we do see some gas lying along this 2/3 line. So if you were to sample some of this gas and fit a correlation to this, you could actually bias to higher slopes. And then we explored varying the initial magnetic field in these simulations. Here is showing weakly magnetized up to very strongly magnetized. You form very different morphologies. These are the equivalent phase space plots for each of these simulations. What's interesting is that I've varied the initial magnetic field by several orders of magnitude. So this is very strong initial field on these parsec scales. This is very weak, less than a microgauss initial fields. And during the collapse, though, a lot of the gas actually follows this 0 to the 1/2 line, which for a plasma beta of roughly a few. And in this very strongly magnetized case, this subcritical case, you actually get, so initially you get contraction just along the field lines first. So you actually get the slope of 0 initially in your contraction. Okay, and then these are some morphologies on CARMA scales. We get some pinching up the magnetic field lines. In some cases, well, in the strong magnetic field case, we don't get a very well-defined core due to the magnetic pressure support. And then we're actually interested in ALMA scales. So here I'll just show you one of the simulations where we follow the collapse down to 100 AU scales. And so this is a large scale box, and we can go down to these scales of roughly, so here on these axes is 3,000 AU on each side, and we see convergent flow. We see evidence of pinching of the magnetic field lines here and here. But we also see interesting morphological features. We see filaments, clumps, and shocks, and then we can predict the velocity components shown in the magenta arrows. And so I'd like to conclude by just comparing the simulated data with observations, and we'll do more sophisticated analysis of these by comparing the histogram of relative orientation between the magnetic field and the density structures, where we find, of course, the classic preferential agreement with magnetic fields and the density gradients at high densities. Okay, thank you.
Questions? Yes.
This is just a very simple comment, but I noticed the slide number that I was interested in is on your slide 25, the strong magnetic field case that actually shows the flat part on the left.
Yes.
Is perfectly consistent with what I was mentioning yesterday.
Yes, exactly. It's the same exact phenomena. It's describing. So if we go back to the Tristis plot here, I believe it's describing this scenario.
So what's interesting is, do you have any prescription to know when the transition occurs from one regime to the other, from the flat part to the power law?
So we're still investigating this, but it roughly the transition roughly occurs once you reach plasma beta of a few.
Over there, Chantal.
Yeah, nice work. In the core where you have the synthetic polarization map with the shocks and filaments, does the core on a 1/10 of a parsec scale also exhibit highly non-thermal motions?
Okay, 1/10 of a parsec scale. So So I think that
It's 10,000 AU, roughly 10 or 20,000 AU.
okay, yes. So we do see interesting filamentary structure on the 10th of a parsec scale, if that's what you mean.
Right. Okay. All right. Thank you.
Okay.
Any further questions? Okay, I'll ask a question. So on the, in fact, the same question that Enrique asked, where you had the very strong field case, I'm surprised that beta matters. I would have thought that it's just controlled by the mass to flux ratio, because it depends on whether, if you're going to start getting the density to increase, it would be, the field to increase would have to be where gravity becomes important. And could you say what was the mass to flux ratio for that run?
Okay, so I haven't done careful calculation of the mass to flux ratio, but perhaps it is that sets the transition density.
Okay.
Okay.
Yeah. Thank you very much. So let's thank our speaker again.